John Kempf, who I was chatting to him earlier, tells me he was a full-time farmer himself at one stage. He hopes to go back farming, but right now he builds himself as an entrepreneur, a speaker, a podcast host, and a teacher. His passion is well-managed agriculture ecosystems and reversing ecological degradation. And he believes in the power of regenerative agriculture management systems to do this and create profit for farmers at the same time. He's founded the Advancing Eco Agriculture, the Crop Health Labs, and Ozadia, as well as the Regenerative Agriculture Academy. And his podcast is called the Regenerative Agriculture Podcast. John, I hope you're there. There you are. How's things?
Life is entertaining. Sounds like you've been having a lot of fun this week. Thanks for inviting me to join.
Well, you're most welcome. I'm going to talk to you a little bit later on in the hour about all your various different pokers in the fire, irons in the fire, so to speak. But I know that you have a particular expertise in brix levels and how farmers can maximize photosynthetic efficiency by maintaining or maximizing brix levels. For people who aren't into bricks per se, the only thing they know about bricks is something that they build a house with. Bring us up to speed.
Well, I'll perhaps provide some context and some background for why photosynthesis is important. I'm going to start all the way at the foundation. So the foundation is about how we think about plant nutrition. And for the last 70 years or so, the mainstream model of agronomy has been based on the idea that plants absorb their nutrients from the soil in the form of simple ions, potassium ions and calcium ions and nitrate ions and so forth. And this was propagated from Justus von Liebig's law of the minimum and the chemistry-based analysis. And I actually believe that in our pathway of looking at ecological and regenerative agriculture over the last 30 or 40 years, or I should say, use perhaps the word organic agriculture, we have unknowingly perhaps been looking at our soil health through an incomplete lens when we rely primarily on soil analysis that look at nutrient profiles. As we've learned from Christine Jones and from James White and others, the plants have the capacity to absorb the majority. In fact, from what I've observed, I believe 100% of their nutritional requirements in the form of microbial metabolites, in the form of amino acids and organic acids and peptides and so forth from the soil profile. And so this is a model of plant nutrition. Instead of thinking about plants absorbing calcium, nitrate, and magnesium ions, all of a sudden, the model now becomes that we need to have plants absorb bacteria and beneficial endophytes and these living organisms from the soil microbial community. And we know from in our work at Advancing Eco-Agriculture, our emphasis has been on producing plants with extraordinarily high quality and disease and insect resistance that are very profitable and they're very high yielding. And our pathway to achieving these results has been by focusing on increasing microbial nutrition. So the next step becomes, how do you accomplish that? How do you achieve plants absorbing nutrients from microbes rather than from simple ions in the soil solution? Because the reality is, if you desire to have these really active microbial populations that are capable of providing nutrients to produce a high-yielding crop, those microbes need to have a food source. And the food source is the root exudates that Christine Jones speaks about, that many others have spoken about. And these root exudates are, of course, photosynthetates that are produced from photosynthesis. So now we come back to photosynthesis. And I believe that this discussion, this conversation and the questions that you've asked are very appropriate, because photosynthesis, harnessing sunlight energy, is the only way we have of bringing new energy, and for that matter, free energy, into the ecosystem. And the perhaps the foundational realization that we need to approach this discussion with is that what we have come to accept as common, what we've come to accept as normal, when we're used to looking at a grassland, we see green plants that are growing, that are photosynthesizing, and what we perceive as normal and common is plants that are photosynthesizing somewhere in the neighborhood of about 15 to 20% of their inherent photosynthetic efficiency. So what happens, and how do those plants behave differently, and how do they grow differently when you increase that photosynthetic efficiency from 20% up to, let's say, 60%, and you get 3 times more photosynthesis? All of a sudden, plants begin growing differently, they begin expressing themselves differently. But one of the key characteristics is that as they have an abundance, a surplus of photosynthate production and sugar production, when you increase photosynthesis by a factor of 3x as you go from 20% to 60% photosynthetic efficiency, that doesn't mean you're going to get 3 times higher yield. You might get 50% higher yield, depending on the crops and the plants that we're speaking about. You might get 100% higher yield, but you're unlikely to get 300% higher yield. So if that additional photosynthesis doesn't express itself as higher yield and as higher forage production, the question is, where does it go? Where do all the extra sugars go? And the answer is, the extra sugars disproportionately go down into the root system and are sent out through the roots as root exudates. That is how we provide the food source for really vigorous and aggressive microbial communities that have the potential and capacity to supply 100% of a crop's nutritional requirements. Because then what happens with these sugars that are sent out through the root system, when we think about sugars being produced during photosynthesis, sugars are simply a bit of an oversimplification, but we'll call them the combination of carbon dioxide and water. So when we think about glucose, as the result of photosynthesis, we have C6H12O6, carbon, hydrogen, and oxygen, a short chain that is 24 links long. And so when we have these sugars sent out through the root system, the reason I am emphasizing and pointing out the elemental constituents is because sugars contain no minerals. There is no zinc, no manganese, no copper, no calcium, and so forth in sugars. And yet, the bacteria and the biology in the soil profile need these minerals to form their own cells and to form their own bodies. So in the process, as plants transmit sugars out into the soil profile, they then extract minerals from the soil mineral matrix and incorporate them into their own cells. And then as this bacterial population cycles, as they're grazed upon by protozoa and nematodes and other organisms, the nutrients, including the calcium and potassium and manganese and all these various trace minerals that are contained within their cells, are now made available to plants, in addition to the biology that plants are consuming directly, as James White has described for us. So when I first started on this pathway 15 years ago of trying to understand plant nutrition and agronomy from a different of how can we really produce plants that have a functional immune system and are resistant to diseases and insects and are very high yielding and healthy, the question that I asked myself is, the mainstream approach at that moment in history by most practitioners in the ecological and biological agriculture space, there were conversations about using soil amendments from the William Albrecht school of thought and the Carrie Reams school of thought. There were conversations about using compost and compost teas. And those were all useful and necessary tools. I'm not discounting them. But they generally all have the perspective that we need to take time to invest in our soils. We need to invest a lot of money and time in remineralizing our soils and building microbial populations in anticipation of some future payoff that we should expect to see crop responses and profitability improvements in 2 or 3 or 4 years down the road. And in the position that we were in on the farm that I was growing up on and that I was running at that point in time, we didn't have the luxury of 2 or 3 or 4 years. We needed an immediate crop response because we had 3 years of disaster, losing greater than 70% of our crops, and we needed an immediate turnaround. And so the question that I asked myself is, how can we provide an immediate crop turnaround? And it's Also translated into the question in our work at Advancing Eco-Agriculture, we focus very intently on how can we make certain that the growers we work with produce and observe an economic return the first year, the first crop that we work with. And that has led us to using foliar applications of nutrients as an entry point, as one of the things that we focus on for one very simple reason. Foliar applications of nutrients I see as a tool to hack the system, because there is an immediate, when foliar sprays are correctly designed, there is an immediate spike in photosynthesis, where you might have forages and grasses with a base level of 2 or 3 or 4 brix, and you put on a properly designed foliar spray and you get this spike up to 12 to 14 brix in a matter of 24 hours. And so from what we have experienced, and kind of the foundation of our work today is to say that using cover crops and using soil amendments and all these different types of cultural management practices that many people talk about as the foundation of ecological agriculture and biological agricultural approaches are extremely important. But the payout and the economic returns take time. Kind of the shortcut to success, immediate success, and for rapid farm turnaround is to use foliar sprays to increase this photosynthetic efficiency from 15 to 20% up to 60% in a matter of a day or two, and then use that accelerated crop growth to fuel the microbial community in the soil system and to start rebuilding soil health. So that's kind of the big picture perspective and the approach that we've taken. And from that point, we can take the conversation in different directions. We could speak about what exactly is brix and how do we measure it and manage it. I could speak about how exactly do you increase photosynthesis? What does it take for a foliar application to be successful, and what is one that is correctly designed? So we can go in many different directions, but I'd love to hear your response on what I've shared so far. What is it that you would like to hear more about?
Okay, so that's setting the scene. I suppose the question that's in my head, John, is, you know, practical applications. I'm conscious a lot of farmers tuning in here, and they're interested. They're either already on the journey towards organic farming or biological farming, or they're interested in getting started on it. And the majority of farmers in Ireland are livestock farmers. They're farming beef, dairy, sheep, and you know, grass is the main crop. It's a low. The only people I've ever heard talking about brix in any serious way before, brix levels, were maybe growers of very high value crops like strawberries or fruit. Is there a way to where analysing your brix levels as a livestock farmer grazing grass can pay dividends for you in terms of extra grass yield or in terms of better livestock health?
So I'll talk a little bit, to answer your question, I'll talk a little bit about brix as a measurement, and then I'll talk about practical application of how do you increase photosynthetic efficiency. So first, when we think about brix as a measurement, I'm not a huge fan of using brix as a measurement tool. It can be useful, and I've explained my thought process of why I'm not a fan of using a refractometer and brix measurements as a management tool in a blog post that was fairly detailed. You can find it on the blog. But the central thesis of why I am not in favor of using a brix meter or a refractometer, as they're called, is because they do not give us the information we need to make management decisions. It's kind of it's a black and white scale to some degree, in that you're low or you're high, or you're somewhere on the spectrum. But if you are low, it gives you no information about what you need to do to increase it. And that is the significant deficiency of the tool. And there are also other challenges in that the brix readings are very highly variable. If you take a reading in the morning versus in the afternoon, they will be completely different because the plants are photosynthesizing during the day. If you take them on a cloudy day versus a sunny day, they will be completely different. So as a result, using a refractometer effectively as a management tool requires a lot of experience. It requires using it a lot. You need to take refractometer readings every day or consistently several times a week for several seasons to get a good perspective on what the baseline is and how the climate and the environment influences it. So those are some of my criticisms of the use of it as a tool. With that being said, the reason brix readings and a refractometer are a useful tool is because they are an analog indicator, not a direct indicator, but they are an analog indicator of photosynthetic efficiency. So if you have a crop that has a brix reading of, let's say, 3 or 4, then it is easy to surmise that this is a crop which is on the low end of its photosynthetic efficiency, perhaps 15 to 20%. Whereas if you have a grass crop with a brix of 15 or 16, it's easy to surmise that this is a grass crop that is approaching 60 to 70% of its photosynthetic efficiency. So we can use it as an indicator of where they are on the scale if we take all of the climatic considerations into effect or into consideration. So those are my thoughts on using the refractometer as a management tool. Now, the question, the practical question, of course, is if we have a crop that has a brix reading of 3, how do we move it to a brix reading of 15? And how do we, and by the way, on forages and grass crops have some of the biggest yield responses to increasing photosynthetic efficiency of any crop, because when we speak about root crops such as corn or soybeans or grain crops or fruit and vegetable crops, the yield potential that these crops are capable of is also limited by the plant's genetics. How many fruit and how many grain seeds is it actually able to set and pollinate and fill? But with forages, this is not the case. We are looking simply at how rapid increase vegetative growth. And there is a direct correlation between vegetative growth and photosynthetic efficiency. So it is possible, from what we have experienced and observed, it is entirely possible to increase yields by 60 to 80% on forages that are at a baseline of 15% photosynthetic efficiency. We get very significant yield responses from increasing photosynthetic efficiency in addition to quality responses. But how do you get there? So to provide some context for how you achieve these results, let's talk a little bit about the photosynthesis process itself. So photosynthesis, in oversimplified version, is plants are absorbing water both from the atmosphere and from the soil, and they're absorbing carbon dioxide primarily from the atmosphere through stomata on the bottom side of the leaf, and they are combining H2O and CO2 to form glucose. So, and of course, the significant inputs, when I started looking at photosynthesis and thinking about how can we hack the system to increase photosynthesis significantly, I started by looking at what are the significant inputs into the system, what is needed for plants to photosynthesize at these higher levels. And I've come up with a group of 5 significant pieces that are important, and some of them are well known and understood, and others are not considered at all. So I'm just going to go through the list of 5 very quickly. The first, the obvious one that we all know and understand is sunlight. If you have limited sunlight, you're going to have limited photosynthesis. The second significant piece is adequate water. We know when it's dry, we're not going to have good photosynthesis. The third piece that is less well understood and appreciated is carbon dioxide. In fact, most crops today on most agricultural soils are chronically deficient in carbon dioxide. They do not have enough carbon dioxide to photosynthesize well, particularly forages and grasslands. So when we think about forages and livestock production, when you look at the ecosystems that are the most efficient at sequestering carbon, at the moment, the authors this white paper, but call reading a white paper a number of years ago where they described the different ecosystems and their capacity to sequester carbon. The most efficient ecosystem known on the planet to increase or to sequester carbon, is a young growth coniferous forest, evergreens, pine trees and so forth. The second fastest is forages that are being managed with intensively managed rotational grazing. So diverse forages that are being properly managed. And the third fastest ecosystem, surprisingly enough, is corn. But another way of looking at this, so we're talking about forages and livestock. So this means that if this ecosystem is so effective at sequestering carbon dioxide, it also means that it is very effective at sucking carbon dioxide out of the air, and that there often is not enough carbon dioxide in the air to sustain photosynthesis. So what this means, in practical terms, we understand that the background atmosphere has somewhere in the neighborhood of about 430 parts per million carbon dioxide. Of course, this fluctuates with the seasons, and it fluctuates based on wind flows and so forth. But we'll just use that as a basic background. And during the growing season, if you have a forage crop on a warm, sunny day in June or July, where it has enough sunlight and it has enough water, this forage crop will pull all the carbon dioxide out of the atmosphere. Well, I'm using the word all. It'll pull the majority of carbon dioxide out of the atmosphere to the point where the atmosphere right above this grazing land drops from 430 parts per million down to, in many cases, less than 100 parts per million. And what this means, this is a very important point. What this means is, and usually, actually, let me add a time factor in here. When the sun rises at dawn and photosynthesis starts climbing, usually carbon dioxide levels will drop from 400 plus parts per million in the background atmosphere down to less than 100 parts per million in about 3 to 4 hours. So this means that for the rest of the day, from that point on, it doesn't matter that the plant has perfect sunlight and perfect water and perfect chlorophyll and everything else is balanced. It means that for the rest of the day, carbon dioxide is the limiting factor for photosynthesis. And this is why in high-value crop production in greenhouses, people inject carbon dioxide up to about 1,100 parts per million. We've identified that at 1,100 parts per million, we get double the biomass and double the yield when everything else is identical. So our goal should be to do that in our grasslands as well. The question is, how do you do that? The way you get carbon dioxide levels to be higher is through microbial respiration. So again, when you start feeding biology, and biology in the soil breathes and respires carbon dioxide the same way that livestock above the soil surface do, you get this flush of carbon dioxide that you can now have sustained photosynthesis through the day. So carbon dioxide was the third significant point that I mentioned. There's two others that I want to expand on a little bit as well, because they apply to direct cultural management practices of what we can do. The fourth element is chlorophyll. And I'm going to come back to chlorophyll in a slightly different framework and talk about chlorophyll in the context of the minerals and nutrients that need to be present to have good photosynthesis with chlorophyll. But then there's one additional element. There is one mineral that is so important that it's worth mentioning by itself, and this nutrient is manganese. The reason manganese is so important is because when water is absorbed from either the soil or from the atmosphere, the first step in the photosynthesis process is the water molecule of H2O needs to be split into H and OH, hydrogen and hydroxyl ions. This process is called water hydrolysis. And the process of water hydrolysis is completely dependent on manganese as an enzyme cofactor. This means that even when you have perfect sunlight, perfect water, perfect carbon dioxide, and lots of chlorophyll, if you have low levels of manganese, then that will be the bottleneck that slows down photosynthesis. And this is a really big deal for one very simple reason. 98+% of all the soil ecosystems and all the plant ecosystems that we have looked at have been chronically deficient in available manganese because of how we have managed them over the last 60 or 70 years. So this is a very important point. First, let me begin. We have abundant levels of total manganese in most soil products. So it's not the quantity of manganese in the soil that is the problem. That is not the problem at all. There are some soils that might be exceptions if you have very sandy soils and so forth. But most soils have abundant total manganese that is locked up in the mineral matrix. And many soils will, when you conduct a soil analysis and send it to a laboratory and get it back, it will show you have abundant levels of manganese, and yet the crops are chronically deficient. And if you want to evaluate this for yourself, it's actually very easy to observe this visual in the field. When you look at a plant leaf or a grass blade, the vein or the midrib should be as...
Okay, John, you're back with us. The wonders of modern technology, or the perils, as the case may be. You were trying to explain to viewers and listeners about the importance of manganese. I think specifically how you could probably pick up on whether there was a manganese deficiency in your forage by looking at the leaf. Yes.
Friday the 13th has no influence over us. We influence it, and we're not going to permit that to happen again.
So say all of us.
When you look at the midrib on a blade of grass or the veins on a leaf, those should be the same color or darker as the section between the veins. And when those are lighter in color, that is a signal of a very low grade but chronic manganese deficiency. So you can easily assess this by walking out into the field and looking at it, and you will find, and this is a universal, this is true of trees and weeds and grasses and forages, it's an almost universal indicator. And there are a few outliers, there are a few crops that genetically have light colored stems, but they are the exception. And so it's very easy, and you will observe when you start paying attention, the majority of the plants that you see express a manganese deficiency. Why is this? This is true because the manganese that is in our soils is present in different oxidation states. And we don't have the time to go into detailed chemistry explanation of what that is going on, but let's just, if we use iron as an example, because it's easily understood, we can have iron in what is called the oxidized or the reduced form, or double positive or triple positive or quadruple positive. And what this means very simply, if you take a piece of steel and you expose it to air and sunlight, that steel, that iron starts rusting, and this rust is oxidized iron. And the key is that plants can't use oxidized iron. They have to have iron in the reduced form. The same is true of manganese. Plants can't use oxidized manganese. They can only use reduced manganese. And there's a longer explanation that I provide on some of my webinars, but what I can just say very briefly is that in most of our agricultural soils, because of the way that we have managed them for the last 70 years or more, because of the way that they have been tilled, and the way that fertilizers have been applied, and the way that limestone has been applied, and the way that we have sprayed them, we have produced a microbiome in the soil profile that has led to all the manganese that is present in the soil, and the majority of the iron that is present in the soil being present in the wrong form. So there is a tremendous amount of iron and manganese in our soil profile, but plants cannot pick it up very well, and when they pick it up, they can't utilize it. So I know the comments that I heard from you are, how can we apply this and at what cost? So I'm going to move on to the last piece and then come back to that. So I spoke a moment ago about chlorophyll. And in the context of chlorophyll, we have observed that there are 4 specific nutrients that that plants need to have enough of. They need to have enough magnesium, because that's the core of the chlorophyll molecule. They need to have enough nitrogen. So we know that there are 3 nutrients which turn plants dark green. And I find it intriguing how these nutrients are used in different industries. If I were to ask you as a group of farmers, what nutrient makes plants dark green? We know that the answer is nitrogen, because we put nitrogen on and plants turn dark green because of the increase in chlorophyll content. If you go to the horticulture industry where they're growing petunias and poinsettias, you ask them what makes a plant dark green, the answer is magnesium, because they use magnesium to turn plants dark green using chlorophyll. If you go to turf and golf courses and so forth, they use iron to do the same thing. And the reality is you get the biggest crop responses if you combine all 3 of those. Both magnesium is the core of the chlorophyll molecule, surrounded by 4 nitrogens, Iron is not a part of chlorophyll, but it is needed to put chlorophyll together. And then, so those are the three important nutrients that plants need to have enough of. They need to have enough nitrogen, magnesium, iron, and then the fourth is phosphorus. And this is an interesting one. Phosphorus is not a part of the photosynthesis process, but it is going to be needed in larger amounts to metabolize all the extra sugars that these plants are going to be producing. So, to bring it really down to how do we manage this in the field, it's quite simple. You are familiar with the idea that if you apply nitrogen, you get a tremendous plant growth response because of the increased photosynthesis that results. But what if you realized that you can get an equivalent growth response from applying not just nitrogen, but also magnesium and iron and manganese to increase photosynthesis overall, and not to produce the negative quality effects that surplus nitrogen produces? So our pathway to achieving these results has been simply to use foliar applications of manganese, to use foliar applications of iron, to use foliar applications or soil applications of magnesium, and foliar or soil applications of nitrogen, simply to make sure that the plants have enough. I'm not, in some agricultural contexts, I'm not suggesting that you need to add more nitrogen or that you need to add more magnesium. Many soils have enough, some soils don't, but those are the specific nutrients that we need to manage to increase photosynthesis to a much higher plateau of performance. And the question that I often get asked is, why foliar sprays? Can't we just apply these nutrients to our soils? And the answer, unfortunately, is no. And the reason the answer is no, and actually let me clarify that. Yes, you can apply magnesium and nitrogen to soils and get a strong crop response. But in our experience, you cannot apply iron and manganese to soils and get the crop response that plants are capable of. Because when we apply manganese or iron to the soil, because of the soil's existing microbiome that has shifted over the last several decades, anything that we apply to the soil immediately reverts to the oxidized form that plants can't utilize. So we've wasted our money. Plants are not getting it. And that they're in the short term, for the first 6 months or a year or 2 years, depending on what state our soils and our soil microbiome is in, we need to use foliar sprays to increase this photosynthesis and to change the microbiome. And then as the microbiome changes, then it is cost effective to apply manganese and iron and so forth to the soil profile, if it is even needed. In many soils, it's not even needed. Think of it this way. I'm advocating using foliar applications as the starter fluid to get the system running at higher RPMs. So I'm not advocating their use as a long-term tool that we need to use long-term in the future, but they are kind of the Kickstarter that initially moves photosynthesis to a much higher plateau of performance and then produces enough energy to start sustaining itself.
So John, am I thinking about a farmer getting out in a sprayer with a foliar feed in the tank, and he needs to go maybe every couple of weeks with this foliar feed out on his grassland, on his pasture?
Depends on the outcome that you desire and depends on where you are when you begin. The extremes that I've observed, so think of foliar sprays and their influence on brix reading as a tool to ratchet up the overall system. So what happens is, if we have grasses that have a brix reading of 3, and we put on a correctly designed foliar spray, that brix reading will spike from 3 up to, let's say, a 12 in a matter of 24 to 48 hours. And then gradually it drops back down. It'll drop back down to a baseline of maybe 4 or 5. It'll be a slightly higher baseline, but it will drop down. The question is, how much time does it take for it to drop back down? On ecosystems that are really challenged, soils that have been very degraded with poor biology, it can drop back down again in as little as, in extreme situations, I've seen it drop back as quickly as 5 to 7 days, but those were on annual crops, not on forages. On forages, that effect, it can take as much as 8 to 10 weeks for it to drop to drop down again. So it is ecosystem dependent. Some soils and farms, it happens in a period of 3 to 4 weeks. Some it takes 8 to 10 weeks. And then you put on, so now that it's dropped back down to a 4 or a 5, you put on a second foliar application and you spike it up to a 14 or a 15. And this time it drops back down to a 6 or a 7. So over a period of multiple applications, the goal is not to increase the peak so much as it is to increase the baseline. So you take the baseline from a 3 to a 5 to a 7 to a 9 and then to a 12. And then when you have the baseline at a higher level of performance, you're now at a space where you don't need the foliar applications anymore because the ecosystem and the biology has changed so much that it can sustain itself.
Have you seen much of an uptake amongst farmers, or has any independent research been done on this by any of the agricultural institutions in the US?
Well, we're talking about several different aspects. Are you asking about the performance of foliar applications or brix readings?
The foliar applications, yeah.
Well, it is well understood that photosynthesis is a significant variable. This is commonly, there are instruments that you can take into the field to measure a gas exchange of how much carbon dioxide is a leaf absorbing and how much oxygen is it releasing. So it's well understood that photosynthesis can vary significantly, and this is included in some studies as a variable depending on what the research is attempting to confirm. So I think it's very well accepted from that perspective. Has the effect of these specific foliar applications and nutrients that I'm describing been studied systemically? Not that I'm aware of. There's probably between 3 and 4 million acres of farmland that we work with that are doing this on scale, and they see the results. They wouldn't really care what the studies say. They would keep on doing it anyway.
That's a huge area. I mean, are you talking about a couple of very, very large operators that are operating across thousands of acres, or is it there's literally tens of thousands of farmers using the products?
We are working right now, I don't keep track of exact numbers, but we're working with somewhere in the neighborhood of 1,000 to 1,200 farms. So it's not just 4 or 5 operations. Yeah.
Yeah, I'm going to throw to Sean McGlowan here.
John, that's really interesting. I just wondered, in that mix, can that be done organically as well?
Yes.
Okay.
Here, quite easily. At least with the organic regulations as they are here in the US. I'm not sure how yours would compare, but I would assume so.
Yeah, and would that mean that you could get away with maybe something like having your nitrogen coming through red clover swards or whatever like that? Would that be?
Absolutely.
Yeah. Okay. Thanks.
Absolutely. Yeah, I'm not suggesting that in each ecosystem that you need to add more nitrogen or that you need to add more magnesium. You simply need to make sure that the ecosystem has enough. And we seldom see nitrogen being a problem. It's the most systemic problems that show up most of the time are low iron and low manganese. And it's important to mention that your soil test will likely show that you have generous levels of iron and generous levels of manganese, but your crop is actually deficient in spite of that.
Well, can I ask you just on that point then, is in terms of which soil test to do to measure that, because there was some discussion over the last week on the standard test, do it, or do you need to go for something more comprehensive, or what would your opinion be on that?
So the approach that we use on the operations that we work with, we use a standard soil test. We also use, are beginning to use the Haney analysis quite consistently on many of the farms that we work on. But the only valid indicator that we have found that measures actual plant absorption of iron and manganese is a plant sap analysis through Nova Crop Control in the Netherlands. So we use that to measure what is the crop actually absorbing from the soil. And we find fairly significant differences in the case of those two trace minerals between what the plants are actually absorbing and what shows up on the soil analysis.
You mentioned a soil analysis, a sap analysis rather. Do all your samples go to the Netherlands for testing?
Yes, we do. We send 1,000 or more samples a week to the Netherlands through the growing season from here.
Wow, isn't it crazy?
Wow. And so that works. So I guess we could do the same from wherever in the world. If they take samples from the US, they'll take samples from anywhere in Europe too.
Yeah, I know some of the
I know
farmers
growers. We're working with growers from Australia and Brazil and all over who are sending samples there.
Okay.
Yeah.
We've got a series of questions in here from viewers and listeners. Philip Reck asks, how can we grow such high yields with such low photosynthetic efficiency? Yeah, and maybe even a broader question is, is the scope in different latitudes and longitudes for increasing the photosynthetic activity variable depending on where you are on the planet?
Well, I would ask that question a little bit differently to the question specifically that Philip asked, which is, if we are producing these high yields at 15% photosynthetic efficiency, what is possible at 60%? I've come to the conclusion that we don't really know what healthy plants actually look like anymore. We don't know we don't recognize what these plants are actually capable of. We have emphasized our agricultural progress and research and development over the course of the last several decades has focused significantly on improving genetics and on improving chemistry, but we haven't really understood the influence of biology and how we can increase photosynthesis to optimize that genetic potential that we have bred and developed. So to your second question of what is the ecosystem context and how is it different in the tropics versus perhaps in Ireland? And the question that we need to ask when we look at these different environments is just simply to ask the question, okay, what is the limiting factor? How are carbon dioxide levels in the atmosphere different in the tropics from what they are here versus sunlight and water? So it should be fairly easy to assess what are the local ecosystem strengths and weaknesses based on the needed resources that it can deliver for photosynthesis.
Okay. Mary McMullen asks, why can we go from 20% photosynthesis to only 60% and not beyond to a higher percentage efficiency? And I suppose it maybe sounds like a funny question, but is there such a thing as 100% photosynthetic efficiency, and what does that look like, and who decided what's 100%?
The answer is yes, you can go to 100%, but to do so requires an ideal environment. It requires perfect sunlight, perfect water, perfect temperature, perfect carbon dioxide, perfect chlorophyll, and perfect nutrition, which happens only in a protected environment. So if you're growing in a greenhouse and you can control all those variables, then yes, you can get to 100%. But in an outdoor agricultural environment, I've started using 60% as a threshold because that is a commonly achievable threshold by most farmers in most environments. Sometimes you can go higher than that for periods of time, and sometimes you can't quite reach that for periods of time because of drought stress or whatever.
Okay. Fran O'Donovan asks, can you increase photosynthesis without an increase in sunlight? I think you've probably answered that as yes. Given our temperature, climate and high latitude. We might keep moving. I think we can take that as a yes. You've got a question there, Sean.
I have one question, he'll kill me if I don't ask this, is David Wallace. We've a statutory limit of 8 parts per million phosphorus in grassland and 10 parts per million phosphorus in arable crops based on the Morgan's test. Would these maximum allowable levels limit optimum forage and crop production?
10 part per million on the Morgan test, and what was the first maximum that you stated?
8 parts per million in grassland and phosphorus.
8 parts per million in grassland. I would say without the inclusion of mycorrhizal fungi, those low levels will limit photosynthetic efficiency. But when mycorrhizal fungi and other phosphorus solubilizing bacteria are present, they will be able to extract phosphorus and supply it to the crop, and you should not have problems.
Okay. I've a question here from Sandy Roberts. In a country where there is no, I think you've answered this
Yes.
already, where there's no SAP analysis, is there any other option?
Yeah.
Go to the Netherlands, the Dutch have it all sorted. And is there, I mean, if this is a whole scene or technology that's taken off, surely these kind of SAP analysis labs would be popping up all over the world?
There are many people who are trying. There's a number of people here in the US who are trying, and the challenge that the Dutch have figured out that no one else has figured out yet, although there are people that are working on it, is how are you consistent? How do you get the same concentration of sap from a tomato leaf or a watermelon leaf that has a lot of moisture as from grass that has very low moisture? So how can you be consistent across species, and how can you be consistent from crops that are harvested when it's comparatively dry versus when it's comparatively wet? So they've figured out a way to be consistent and to get highly repeatable data. Other laboratories are trying to figure that out as well, but it's still a work in progress.
Okay. I have another one here from a viewer, John, just wondering if you can explain in greater detail the source/sink concept.
So if I'm understanding the question correctly, it relates to the photosynthesis source versus sinks. So plants have, it's commonly described as 3 different sugar sinks, but I would like to expand that to say that there are 4 significant sugar sinks. So the one sink is the new growth, both new growth at the top of the plant, the new shoots and new shoot growth, where sugar is actually going to these new shoots to provide both an energy source and the building material to develop new growth. The second significant sink is the growing root tips, for the same reason, where the sugars are also used as an energy source and as a building block for new root growth. The third significant sink is the fruit, and seeds and so forth, grains. And the fourth sink, and I'm separating this out distinctly for a reason, the fourth sink is the root exudates. So depending on the plant and the stage of growth, Christine Jones and others have spoken about how really healthy plants will transmit as much as 70 to 80% of their total photosynthetic production out through the root system as root exudates to feed soil biology at different stages of plant development. So those are the 4 significant sinks, and then there is really only one source, and that is a green, actively photosynthesizing leaf.
Okay.
Okay.
Have you got more questions there, Sean?
Yeah, I do. Philip Reck asks, can you explain the role of calcium and boron within the plant and how it raises brix levels?
In 30 seconds or less. Well, let me just say that I'm not going to include calcium because calcium is so foundational to so many different things in the plant, and I don't think of calcium as having a significant direct influence on brix levels. It is foundational, of course, just to maintain overall plant health. But boron does influence sugar movement in the plant very significantly. So boron is, you can think of boron as the train switchmaster or the dispatcher, where boron tells the sugars where to go within the plant. So one of the tools that we use a lot is if we have a crop that we want to mature more quickly, or if we have forages in the late fall that are not going into dormancy very well, we will put on a foliar application of boron. And that foliar application of boron triggers the plant to move the sugars out of the leaves to the sugar sinks. So if we're talking about forages, that means moving the sugars down into the crown and down into the root system. If we're talking about grains, that's moving sugars into the fruit or into the seed. And so as a result, what happens with forages, we've experienced this many times. If you put on a strong boron application, the forages will turn brown much more rapidly on the treated side than they will on the untreated side. And in extreme cases, it may look almost as if though you have herbicide damage. But then the following spring, the sections that were treated with boron that were brown in the fall will grow back much more vigorously and lush than the untreated area, because all those sugars now move down into the crown and they provide a lot of energy for spring regrowth.
Okay.
Okay. that you all out, Sean?
No, I have. Nigel Gill has asked, very simply, he says, can you raise brix levels in cereals? Sorry, how to raise brix levels in cereals?
It's the same. The principles that I described are true for all crops, any green plant that photosynthesizes. And I would just add for our audience, if you have any further questions that we haven't had time for, you can always send me an email, and if it's an in-depth question that I need to respond to, I'll write a blog post about it, or I can respond on Twitter. You can find me on Twitter as well, and I'll respond there also. Really
appreciate that, John. I'm conscious that we are coming to the end of our talk, and I did want to ask you about your podcast and your other activities. I mean, would you bill yourself mainly as an advisor, an agronomist at this point in your career, or are you split between lots of different activities?
I can never hold still. I'm always doing something else new, and I really enjoy the creativity. So my primary work day to day is that I am a consultant for the consultants. We have an amazing team at AEA, and when they encounter challenges that they can't figure out, I work with them to figure out what's happening and what's going on. But the newest project that I've been working on that I'm really excited about, and I do want to take just a few seconds to tell you about, is an online discussion platform that is called Kind Harvest. You can find it at kindharvest.ag. Think of it, it is a platform that is Facebook plus Ag Talk that is specific for agriculture, specific for farmers, because I believe, and you can see this in the work that I've done on the blog and on the podcast, I believe that collectively, we as an agricultural community have all the knowledge and all the wisdom that is needed to bring agriculture to a very different place very quickly. And the most powerful thing we can do is to get together and share information, which is exactly what we're doing here at this conference. And that is the intent of Kind Harvest, is to provide a space for thoughtful conversations which don't seem to happen very easily on Twitter and Facebook. They're not the place for thoughtful conversations.
You can sing that. And that's free to join? There isn't a fee or whatever to join in the conversation?
Yes, there is a fee to join, and the fee to join is there deliberately, obviously, so for two reasons. One is our customers are not the product. So there is as of yet, there is no advertising, and there will never be advertising in the people's newsfeed. We also want to provide a barrier and a gateway to keep the trolls away. We want to have high quality conversations. And if that isn't worth $8 a month, then you're probably not the right person to join the conversation.
Okay, very good.
Yeah.
And of course, you're involved in a podcast. Is that a weekly thing, or just whenever you get time?
Podcast, we try to do every 2 weeks. We sometimes don't hit that quite, but it's about 25 or 26 times a year. And then you can also, if you want to find all of my work, the place to where we bring it all together is on my personal website, johnkempf.com. I also do a webinar monthly, and during the winter months, it's twice a week. I frequently host Ask Me Anything webinars where I just respond to people's questions, and you can find out about those by subscribing to the blog. And I've been blogging 3 to 5 times per week, except for a recent month break that I took, but 3 to 5 times per week, just short 60-second snippets on things that I'm thinking about and working on and related to agronomy and plant health.
Great. Well, we really appreciate you taking the time out of your busy schedule to talk to us today. A fascinating insight. And I must say, I was slightly mesmerised by your beard as well. You may need to share some facial grooming tips with us, how we can up our game. I think you're at another level there in that regard as well.
That's just optimizing genetic expression.
There you go. Okay. John Kempf, thanks so much.
Thanks a million. That was great. Thank you.